So the next topic we're going to talk about is we're going to go through quickly the object-oriented design of our expression tree processing app. And the purpose of this, again, is to give you the big picture view of what we're doing from a design perspective. We're also going to try to focus on what design is relative to implementation, because those are two sides of the same coin, but they're different sides. And that will then lead us to the next topic, which is the topic about patterns. So we're going to talk about the object-oriented design of this program. And before we do that, we, of course, have to quickly recap what is object-oriented design. Now, my guess is you've taken some courses thus far focusing on Java and or C++, maybe Python, depending on what you've taken. And so you've probably learned about object-oriented programming. And you've learned about features like classes. You've learned about features like methods, which are basically the data abstraction features. You've learned, undoubtedly, because we've talked about it, generic programming, which is really about parameterized types. We've talked about things like inheritance and dynamic binding, things like C++ support for virtual methods and different types of inheritance, access control specifiers like protected and public and so on. We really haven't stepped back a whole lot and talked about the design elements that underlie or actually overlie those language features. And those are essential to making sense of what object-oriented design is. So object-oriented design, of course, is basically a method for planning how you put together the elements of a system of interacting objects in order to solve some set of software problems which have functional and non-functional requirements. And the key themes, the key concepts that underlie object-oriented design are abstraction, encapsulation, extensibility, and polymorphism. And what's interesting about this is that all of these things have correspondence in features like C++ classes, or C++ access control specifiers, or C++ inheritance syntax and semantics, C++ dynamic binding and virtual methods, and so on. But what's important to understand is that these design concepts are not wedded to C++. So you can have the same design concepts and you can apply the same design patterns and come up with implementations in C++, in C#, in Java, in C, in Python, in assembly code, if you're really brave. And the point is that you can have different groups of language features from different types of languages, all embodying the same concepts and principles in an object-oriented design. And so that's why it's important to think about design as design qua design, as the philosophers might say, to think about that separate from any given implementation language. And if you're like many people, you've grown up learning Java or Python or C++, and you tend to be happy learning how to think in terms of those abstractions and features. And that's great, but design is broader than a language. It's more about how the pieces fit together. So abstraction, of course, is all about stepping back from unessential details and thinking about interfaces and common APIs, application programming interfaces. Encapsulation is about taking those abstractions and hiding implementation details or representational details so that if things change, nothing breaks from the client point of view, the user point of view. Extensibility is making it possible to take what exists and build upon it in order to make something work that combines other things that are already there. Those would include features, of course, like parameterized types and inheritance. And then finally, polymorphism is about dynamic binding, about being able to decide at runtime which method on which object to dispatch based on the runtime type information in your system. So that's a 3 or 4 minute description of decades of thinking about object-oriented design. And even nowadays, when functional programming and generic programming is becoming important, or has probably become the dominant paradigm, object-oriented design is still crucially important to handle the architectural aspects of complex, larger scale software systems. The key abstractions, the key themes in an object-oriented design are the concept of hierarchical data abstraction, where you have base classes, abstract base classes, superclasses that are then going to be used as the basis for stable APIs, application programming interfaces, that are capable of being customized or refined through inheritance and dynamic binding. So the whole point is to have these stable interfaces that you then can use as the basis of your classes and objects, and then be able to customize them through inheritance to get different implementation properties. So you can see here as an example, we have the concept of an iterator in C++, and then we can define a whole bunch of different strategies for iterating over a collection, in our case, a collection of nodes in our expression tree. And this way of doing things is often called the Liskov substitution principle, or LSP. So if you take a look at the link at the bottom of the page, you can learn more about this particular aspect of software. There's other cool principles like the open-close principle and so on that we'll also talk about. So the key thing to note is that in object-oriented design, the way that you orient the decomposition of your software into pieces, into components, is based around classes and objects rather than around functions that correspond to actions. That's an algorithmic way of doing things. Now, of course, we have functions, but they aren't the basis of our decomposition. The key theme with an object-oriented approach is to emphasize high cohesion. In other words, methods that belong to a common abstraction are put together in a class, perhaps an abstract-based class. And then we also have low coupling. So you want to have the classes be as decoupled as possible so they don't have dependencies on each other. And if they do have dependencies, you want very loosely coupled dependencies so you can plug and play things in a more natural way. And the reason why this is important, of course, is first, it helps to reduce the surface area of understanding any given piece of componentry. So if you have a class that has a half dozen methods in it that are cohesive, you can probably get your head around that. If you have a class with 300 methods in it, then you're really at a loss to try to figure out what the heck this class does. And oddly enough, there are abstractions today that are incredibly popular that literally have hundreds of methods for each class. And a good example would be the concept of reactive streams and reactive programming, which is a very popular paradigm for Java these days, which I love, but you really have to spend a lot of time figuring out which of those 300 methods in observable or flux or whatever is meaningful for your purposes. And it gets pretty daunting at first. So in an object-oriented design, we associate actions with objects or classes, which then are used to make objects. So we don't associate these things with standalone functions a lot. Now, having said that, of course, STL is all about algorithms that are standalone functions, but we already know that STL is not really an object-oriented design. It's generic programming. Well-designed object-oriented programs will group the classes and objects together using patterns to guide what goes where and how the interfaces and dependencies are reconciled. And then they're integrated or combined to form something called a framework. And we'll spend a lot more time shortly talking about what a framework is. In a nutshell, a framework is an integrated set of classes that collaborate to provide a reusable architecture for a family of related applications. And pretty much everything in today's programming landscape in the ecosystem of software development in 2020 and beyond is based on frameworks. So if you program with Java, you're using lots of frameworks. If you program with Android, you're using lots of frameworks. If you program for iOS, you're using lots of frameworks. If you're programming an embedded system controller that monitors a pacemaker, you might or might not be programming with frameworks. I recommend you do program with frameworks, but as you get into the more resource-constrained part of the world, the frameworks tend to be more fewer and farther between and not as standardized. As you get into enterprise computing, as you get into GUI, graphical user interface computing, as you get into all kinds of other interesting domains that are crucial, air traffic management or whatever, you will find frameworks galore because it's the only way to really handle, not the only way, it's a very effective way of being able to scale up to deal with complexity as your systems get bigger and more complicated. Okay, what I'd like to do now is give you an overview of the object-oriented design of the expression tree processing app. And as we'll see here, this whole design is based on modeling of classes and objects in the expression tree domain. And that's a perfectly good domain. And of course, because we're trying to be as forward-thinking as possible and as generalizable as possible, we're going to be applying commonality and variability analysis to determine what the stable parts of our interfaces and classes are, and then also how to have variation in a common way. And that really is the gold standard of software design. So how do we do this? Well, first of all, we model our tree as a collection of nodes. So you can think about an expression tree as being a collection of nodes, and those nodes have different types. There's leaf nodes that have no children, there are unary nodes that have a single child, and there are binary nodes that have two children. And that's very important to think about in our design. Our design is going to embody the domain of expression trees. And then we're going to take that modeling and we're going to represent it using the creational capabilities in a language like C++, using classes. And we're going to have a hierarchy of classes, and each class that's in the hierarchy will capture various properties of the nodes. So for example, you'll see if you look even very quickly at this diagram, you'll see that we have different types of nodes with different arities. We have unary nodes. We have binary nodes. We have some nodes that have no children at all. And so a leaf node, as you can see, has no children. Composite unary node has one child called composite negate node. And then it's also used in this particular realization to implement something called a composite binary node. We'll talk about alternatives to that later. Composite binary node has a bunch of children: composite add node, composite subtract node, composite multiply node, composite divide node, and so on. And these nodes in the tree map nicely onto the abstractions that we identified when we modeled our domain. In fact, it's really a one-to-one mapping, and in many cases are very close to one-to-one mapping. And then what we're going to do is we're going to apply a whole gaggle of gang of four patterns that will help us design a framework that will make it easy to develop and extensively evolve and sustain our expression tree processing app. So of course you can look at the Gang of Four book to see the patterns, and we'll talk about them. But what we're going to end up with is a design that looks like this, where the classes that we have, which are shown here as UML structure diagrams, are then representing different roles and relationships in a bunch of different patterns. So this particular example demonstrates the composite pattern, the bridge pattern, the iterator pattern, the strategy pattern, and the visitor pattern. And there's lots more. And it shows how the different groupings of classes correspond to different pieces of those patterns. Now, at this point, I don't expect you to make a whole lot of sense out of this diagram because you may not be familiar with these patterns. But I assure you, as we go through these things over the next few days, by the time you see these pictures again, they'll make a lot more sense to you. So this, of course, then leads to the next topic, which is crucially important, which is that of frameworks. And I mentioned before, a framework is an integrated collection or set of software components that collaborate or work together to provide a reusable architecture for a family of related applications. So the key terms here are integrated, collaborative, reusable architecture, and family. And what that means is it's not just a one-off, it's a combination of things, and you come along and customize what's there to make something that's specific and refined for your particular needs. You can take a look at this link at the bottom of the page. I wrote this article back about 25 years ago for the Communications of the ACM, talking about what frameworks are. And it was true then, and it's still true today, which is cool. So let's talk about some of the characteristics of a framework. There are three primary characteristics of a framework that differentiate frameworks from other forms of systematic reuse, such as a class library, such as the standard template library, which is really not a framework per se, it's more of a class library. And so let's talk about those three different categories of things. And by the way, if you look at the link at the bottom of this page, it also talks about these characteristics as well. So characteristic number one, inversion of control, or IOC. And inversion of control basically says the framework owns or controls the thread or threads of execution. There could be more than one. Let's assume there's one for the discussion. And rather than having the users decide what to do, you turn over control to the framework. And the framework then decides how and when to run application code using a technique known as a callback, sometimes referred to as a hook method. We'll talk about this when we talk about patterns like the template method pattern or the strategy pattern later. So you define your classes and then you connect them with the framework and it calls you back. So a good example of this that you might or might not be familiar with is in Android, where there's a framework called the activity framework that handles user interface events, button pushes and gestures and networking I/O and other forms of input. And there's a mechanism called a looper, and it runs a loop waiting for events to come in. And when an event comes in, it dispatches a callback on a handler, which then dispatches a callback on a runnable, which is supplied by an application developer to do something in response to the event that occurred. So that's a very common thing to do in Android. The inversion of control concept is often humorously referred to as the Hollywood principle. And the Hollywood principle says, don't call us, we'll call you. So back in the days when people had respect for Hollywood directors and producers, perhaps that respect has been tarnished of late, but back when they were the ones running the show, there was the joke that don't call us, we'll call you. So if you wanted to get a part in a movie or be a part in a show, you'd wait for the director to call you or the producer to call you. And that was the joke. Don't call us, we'll call you. And if you look at the link at the bottom of the page, you'll see a description of the so-called Hollywood principle written by the late, great John Blasides. And he talks about this as being one of the key themes in a framework is inversion of control, or the Hollywood principle. Another key capability in a framework is the concept of domain-specific structure and functionality. So unlike traditional class libraries, such as the standard template library, that have a lot of really generic things like sets and maps and lists and vectors, and if you think more broadly, strings and time and date objects, all those very generic, very domain-independent constructs and concepts. A framework focuses on domain-specific structure and functionality. And there are different types of domains. There are domains that are application domains, like the domain of social media. There's domains of electronic stock trading. There's the domain of mobile apps. Then there's also what we might think of as infrastructure domains, things like the domain of graphical user interfaces or databases or networking and so on. All of these things have domain-specific structure and domain-specific functionality. And what a framework tries to do is it tries to embody those things so that you can get closer to solving your problem by leveraging artifacts that someone wrote, intending them to be systematically reusable. And again, let's just use Android as the example. People can write some really amazing mobile apps very quickly using Android or using iOS for that matter, that back in the day would have taken long amount of time and effort to do. It would have taken years. And nowadays you can crank these things out, after you take a 5-week MOOC, you can be cranking out Android apps left, right, and center. So it's really productive to learn how to use these capabilities. So what a framework does, what its domain-specific structure and functionality allows you to do, is it allows you to write apps that systematically reuse the components in the framework. And then the third piece of the puzzle for what makes a framework is the concept of semi-complete applications, where you just have to come along and plug in your capability. And the way you do this is through things called hook methods. And a hook method is typically implemented as a virtual function, although it, of course, could also be done with other techniques as well, like pointers to functions or functors or other mechanisms, where the framework does almost everything, but there's certain parts where it just doesn't know what the application wants to do because it's not an application. That's your job as an app developer. And so what it does is it calls out at certain points and expects you to give it something to do that's very specific and very concrete. So that's what's known as a hook method. And we'll talk about patterns like template method and to some extent strategy that can be used to do this. And therefore what the framework does is it mediates the interaction amongst all the common abstract portions that are very reusable, provide you with structure and functionality, and then allow variant capabilities to be added to handle what the user's need for their particular requirements. So it's basically about customizing. So a good example of this in the context of Java is the concept of a Java runnable, which is an abstract interface that can be implemented and then passed off to a thread or a thread pool in order to execute. Of course, there's also gazillions of examples in C++ as well. So a good example would be the sort algorithm, where it's semi-complete and you can pass in different functors in order to determine or guide the way in which comparisons are made. That's another very simple example in the context of C++. So we, of course, are going to show how to do all this stuff in our expression tree example. And we're going to do it by building an app-specific framework. And our app-specific framework, naturally, will be a framework that's oriented towards the design and implementation of expression tree processing programs. And you'll see here, this is just a little tiny snippet that we looked at earlier for iterating through all the elements in an expression tree and printing them. And what's interesting about this particular example, and we'll see it again and again, is that it combines a whole bunch of patterns. It combines half a dozen gang of 4 patterns, including factory method, bridge, composite, iterator, strategy, and visitor, in about 3 or 4 lines of code. So this is what we often refer to as high pattern density. And high pattern density is an extremely powerful concept that you'll get a bit more experience at in this course, but which will let you go on to other courses and write software that's much more intentionally designed and implemented than would have been the case before. And of course, we'll also apply these things in the context of off-the-shelf frameworks. So in our case, we'll be doing it in the context of C++ STL, which is this sort of class library on steroids that often approximates framework-like behavior, even though it doesn't use the classic framework features you find in C++, like inheritance and dynamic binding, but it does give you a lot of the properties of frameworks. The main thing that STL doesn't do that a proper framework does is it doesn't really have a whole lot of inversion of control. I mean, there's places where you pass in a functor to an algorithm, and in that sense, the algorithm takes over the control of the flow through a range, but the concept of dynamic binding isn't really there. So it's kind of along the right lines, but it's not quite as advanced as a proper framework. But we're going to use it in order to simplify our app-specific framework. And of course, if we were programming in Java, we would be using things like Android in order to be able to get a true off-the-shelf set of frameworks. Speaking of which, I teach some other classes at Vanderbilt on concurrent object-oriented programming and parallel functional programming, all of which use Android extensively. So if you're interested in learning more about Android and learning about how to build apps and doing it in a really cool concurrent and parallel way, keep an eye out for those courses. I teach them in the spring and the fall. One of the consequences of the way we arrange things here is that the complexity is going to reside in the APIs, which are stable, the structure, which is stable, rather than being in the algorithms, which are variable. Now, this may or may not make a lot of sense yet. You may not see the virtue of doing this, but when we get done with some examples of patterns, I'll show you how to compare and contrast a pattern in object-oriented design with a very classic algorithmic decomposition, and then you'll see why we don't want the complexity lurking in the algorithms, but instead we want complexity to be bundled up and encapsulated and abstracted in the structure and the APIs.